This is Cranky Calculus. We are here to take the edge off, and if you want to see more videos like this where I just go over entire units, please like and subscribe and ring that bell, and I can go ahead and start tackling some of these problems for you. Maybe I explain them a little bit differently than what you're used to, but let's go ahead and see what we got here. So first off, we're going to find the limits using a graph. So for this first one, we're going to find the limit as x approaches 0. So every time I do a limit graph problem, I think of it this way, is if myself and a friend are on different sides of this path, do we come together and meet each other? So if I'm on the left side of this path, and I'm walking and my friend is over here, if we keep walking, will we meet each other up on this path? The answer is yes. We both meet each other on this path, and we meet each other at the height of 1. So this is equal to 1. Okay? Now, for this next one, as we approach 1, if I'm approaching 1 from the left side, this is me on this path. I kind of got shorter in that picture. It happens. Wait till you get married. That's when you start shrinking. And then my friend is on this path as we're approaching 1. So this person's walking this way. I'm walking this way. Are we going to meet each other? The answer is no. So this is a does not exist. Every time you say does not exist, you must give a reason. And your reason is going to be that the limits from the left side of f of x and the right side do not equal. Okay, so if I want to be more specific on what this is, well, on the left side we're approaching the height of 0, and on the right side we're approaching the height of 1. So that's why they do not equal. Next problem we got going on here is we're looking at 4 to the left. Now this is a one-sided path, so it's just me walking now, and it's kind of steep as I'm walking up and up and up and up. And I'm going to keep going up and up and up forever because there is a vertical asymptote, so this is going to be positive infinity. Positive sign is optional, but I like to put it to it's definitely guaranteed. By the way, just so you know, that is an answer that technically does not exist because it's not a real number, but I want to be as specific as possible just because it's best to do that when you're doing any type of work like this. Here comes a tricky one. It's a composition problem. I'm going to kind of erase what I got so that we can use this graph a little bit better. So I'm looking for the limit as x approaches 0 of f of x. If you were to plug in a 0 into here, you would get f of 0 is 1, and then at 1, you would think it does not exist. But this is how we have to think of it. We have to think of, as we're approaching 0, it's again, me and my friend. We are coming and we're approaching. Since this is a composition function, as we're approaching from below the point. We're at the bottom of this hill right here. We're approaching at the bottom. So this is equivalent to the limit as x approaches 1 to the left of f of x. It's 1 because we're approaching 1 on this hill, and it's left because we're both on the bottom. If we were both on the top of above that point, then we would be looking at 1 to the right. But since we're below, we're at 1 to the left. Now if we look at 1 to the left, that is going to be this value right there. So this is going to equal 0. Moving on here, we have a piecewise function, and we want to find the limit of, this should say g of x. So let's connect that to g. So to find the limit as g of x, x approaches 0 of g of x. So what we're going to do here is break this up into two limits. We're going to do the limit as x approaches 0 to the left of g of x. And if you look at our piecewise function here, that's going to be the top piece. This is going to be our left side because we're looking at x's which are less than 0. So we're going to look at limit as x approaches 0 from the left of x squared minus x. We're going to plug in a 0, and we're actually going to get 0 minus 0, which is 0. And let's look at the right path, which is going to be this bottom one. This is the right path. And if we do that, we're plugging in a 0 from the right into sine of 0, or pi times 0. Pi times 0 is 0. Sine of 0, you should know this, is 0. So these are both equal. Since these are both the same, this is going to be equal. Okay. Number 3 here, this is a limit one where we're going to get this to be in the form of 0 over 0. If we plug in a 1, we're going to get 1 minus 1 on top, 1 minus 1 on the bottom. We're in the form of 0 over 0. We do not want to write down equals 0 over 0 because that is incorrect. But what we want to do, and the problems like this, we want to factor and cancel if we can, or think of something else. This one does not factor, but we can multiply by the conjugate, which will create a situation where we can start to cancel some things out. So if I multiply by the conjugate here, that's going to be x plus root x on top and on bottom. I'm going to get x plus root x. That's going to give me the limit as x approaches 1. The top becomes x squared minus x. And that's going to happen because of the conjugate. The middle terms do cancel out. And I'm going to leave this x minus 1 on this lonesome here because I think I can start to find some things that's going to start to cancel out. Now, if we notice, we do factor now on the top, so this is mathematically equivalent to the limit as x approaches 1. The top does factor to be x minus 1. Bottom is x minus 1, x plus root x. Now, these x minus 1s do cancel out, so they're gone, and I'm left with the limit as x approaches 1 of x all over x plus root x. I can plug in a 1 right now, and I'm going to get 1 over 2. Perfect. I'm not in the form of 0 over 0 anymore. Again, if you want to see more videos like this, you're going to need to like and subscribe, and I'll be more than happy to make some more videos to help you study. Number 4, use the definition of continuity to find the value of k and m that will make the function continuous everywhere. So here's a continuity problem where what we're trying to do here is just quickly figure out how am I continuous. Well, what we want to do here is, for using this definition, we want to look at each piece and make sure that they are equivalent to each other. So I'm going to do this like this. So for this blue one at 2, I'm going to do 2 at blue down here. I need to set those blues equal to each other because they share the same piece at 2, and also plug in an x equals 2. So at my x equals 2, if I'm looking at the left and the right, left versus the right, I'm going to plug in a 2, and I'm going to get k times 2 squared plus 1, and set that equal to k times 2 plus m. So this is going to give me 4k plus 1 equals 2k plus m. And I'm kind of stuck right there. There's nothing else I can do. I just have one equation, 2 variables. I need to figure out another equation with the same 2 variables. And I can do that with 3. So at 3, I'm actually going to underline this now in red. I'm going to plug in a 3 in the top and the bottom there. The top piece versus the right piece. So again, at x equals 3, I'm going to have the left versus the right. So I'm going to go k times 2 plus m equals, so not 2, it should be 3. 3 squared minus m times 3, which is going to give me 3k plus m equals 9 minus 3m. Okay, now I have my 2 equations. I'm going to clean these up a little bit. I'm going to rewrite blue here, subtract the 2k on both sides, and just put all and the m's on the other side. I'm going to get this to be 2k minus m is equal to -1. And this one right here, just cleaning this one up just a bit, I'm going to get 3k plus 4m equals 9. We have 2 options here. We can either use substitution as a method to solve these equations, or we can go ahead and use elimination. I do think it is kind of easy right here to go m equals 2k plus 1. That might be the better route. Probably didn't need to do that step right above it. And I'm going to substitute that in right here so that this becomes now 3k plus 4 times now my blue 2k plus 1 equals 9. So now we solve. I'm going to end up with, on this side, 3k plus 8k, which is 11k, plus 4. That's me distributing that all the way through and combining like terms, equals 9. And then when I solve for k, I'm going to get k to equal 5/11. What a beautiful number that is. And I'm going to plug that 5/11 back into m. So when I plug that back into m, I'm going to get m equals 2 times 5/11 plus 1. Really, I don't care too much about the simplifying part. I'm going to get 10/11 plus 1, which is equivalent to 21 over 11. Okay, so those are my k values and my m values. All right, next one right here. Let's go ahead and consider f of x and g of x. So f of x is a square root function of x. G of x is cosine of pi x. Must f of x equal g of x on the interval from 0 to 1. So to consider this is going to be an IVT question. Okay, I'm actually going to look at f of x minus g of x. Set that equal to 0. That way, I'm going to use 0 as my k value. And I try to find this between 0 and 1. So I got to go through several steps here. First step is that we have f of x minus g of x is continuous. Now, how do I know that? Well, if I have two continuous functions and I add or subtract them, we're going to have continuous functions. So square root of x is continuous on its domain. Cosine of pi x is a periodic function, and that's going to be continuous as well. So this is continuous on 0 to 1. Second thing here is let's find out what f of 0 minus g of 0 is. So again, we're looking at f of x minus g of x being my actual function I care about, and we're just seeing is one value negative at 0 and 1, and is the other value positive between 0 and 1. So plugging in f of 0 and g of 0, that's going to give me f of 0, by the way, is going to be root 0. G of 0 here is actually going to be cosine of 0, which is going to give me 0 minus 1, so it's going to be negative 1. Now, I'm going to compare that to, does this equal f of 1 minus g of 1? Well, that's going to be root 1 minus cosine of 1 times pi is pi. So root 1 is 1 minus cosine of pi, hopefully you know that, is negative 1, so I'm going to get 2. So are these equal? They certainly are not, so I'm going to put the does not equal sign right here. Step 3, k, which is 0, 0 is between negative 1 and 2. So even though we can't solve for this value, we don't have that knowledge. Calculators can totally do it. We cannot. But it is true that square root of x does equal cosine of pi x somewhere between 0 and 1. So must there be an interval? The answer is, or must there be a value where that happens? Yes, by IVT. You don't need to state IVT, but I will just so you can see why this is working. Again, this was an IVT problem. Moving on down here to number 6. Find the following limits at infinity. So as I do these, I might do these a little bit differently than what your teacher does. What I do for values at infinity is for every ratio problem, I try to find out what's growing the fastest on the top versus just the bottom. So for this one right here, for A, this is equivalent to the limit as x goes to infinity. Oops, sorry. Life happens. X goes to infinity. What's the fastest growing function on the top? It's going to be the 3x squared. Fastest growing function on the bottom is going to be the negative 5x squared. Make sure that function term. I want to refer to those as terms. So those are the fastest growing terms on the top and bottom. Those x squareds actually cancel out, and I'm left with 3 over negative 5. That kind of just looks ugly. I like to pull that negative out in front. Make it look like this. Okay? Next up, super similar problem. Actually, I even saw one of my students, I'll do it the way they did it, because I liked it a lot from a test they had recently, is on the top here, they had root 3x squared. And the bottom, we have 8x. Those are the fastest growing terms. Now, I have to include the square root with this. I'll make that line a little bit shorter. Because the square root's part of that term. Now, what is the square root of x squared. That is equal to the absolute value of x. And since we're going out to infinity, this is going to equal x. So this is what I saw my student do, which I liked it, is they then rewrote this as root 3 times x. So now it becomes over 8x. Okay, so since we're going out to positive infinity, that produces a positive x. If I were to flip it and make that negative infinity, then that would produce a negative x. But now these x's do cancel out, and I'm left with an answer of root 3 over 8. Again, do not forget to like and subscribe if you want to see more videos like this. Here we go. C, fastest growing term on the top. Now we have an e to the x and we have an x squared. Exponentials are going to grow faster. So on the top we get 2 e to the x. On the bottom, what do we got here? Okay, I see a negative 12 e to the x. Those are the fastest growing terms from the top versus the bottom. So that x to the 9th, even that's going to grow pretty quickly. E to the x as an end behavior is going to approach infinity a lot faster. So these e to the x's cancel out, gives me 2 over negative 12. Let's clean that up a bit. Negative 1 over 6. Last one here. And as I'm doing this problem, I notice the top here grows the fastest with the x to the 12th term, and the bottom here we have 3x to the 9th. Now if I do simplify this, I'm going to be left with x cubed on top over 3. Now if you know what x cubed looks like that. So our end behavior to the right is going to go to positive infinity. So it really helps know what these graphs look like. Really, or you can just think about plugging in a large and negative number, or sorry, large positive number, and since it's being cubed, it's just going to make it even larger. So it makes sense that it goes to infinity because our term on the top is larger. All right, let's close this review video out with some trig. Here we go. Please do take note. It is super important that you know this property. So limit as x approaches 0 of sine of x over x is 1. The reciprocal is true as well. The limit as x approaches 0 of x over sine of x is also equal to 1. So what we want to do here is looking at A, I see a 3x on top. In order for this to work, I need there to be a 3x on the bottom. I already see a x down there. So I'm going to real quickly cheat a little bit here and rewrite this. So I'm going to get sine of 3x over x, and what's left? I have 4 over 5. I took that 4 in the front and I just kind of rearranged everything. So now I need to make sure that there is a 3x on the bottom so that my argument inside the sign matches the denominator. In order for that 3 to go down there, I have to actually multiply the top by 3 to make this symmetric. So now I have that sine of 3x over 3x, and this is equivalent to 1. Actually, I'll do this in a different color. This is equivalent to 1 times 4 times 3 over 5, and that's going to give me an answer of 12/5. Last problem here. Again, do not forget to like and subscribe if you want to see more videos like this. I can help you out with your tests. If you were to plug in a 1, you're going to be in the form of 0 over 0. So we don't have exactly the same argument like we do in the blue up here. So what I can do is I can factor this top to make it look better. So I'm going to get x plus 1, x minus 1, all over sine of x minus 1. And when I do this, you're going to notice here that I have sine of x plus 1, sorry, I have x minus 1 all over sine of x minus 1. Those are equivalent. If I were to plug in a 1, I would be in the form of 0 over sine 0, which I said if we're in that form with our limit statements, that's actually a hole. It's a hole with a height of 1. So it's equivalent to saying that this is going to be x plus 1 times 1. Because again, that what I circled in pink there is in the form of 0 over sine 0, which is equivalent to 1. So now I can just do a direct plug-in. 1 plus 1 times 1 is going to give me a 2. Again, do not forget to like and subscribe if you want to see more videos like this.